Hello eDrive's embed friends. Understanding the current and speed control techniques for DC motors is very important because these techniques are directly applicable to the AC motor control. An electric motor is an electromechanical device that converts electrical energy into mechanical torque. As a torque-producing device, the electric motor needs to have its torque controlled as a priority. When the torque produced by the motor is applied to a mechanical load, the torque will change the speed omega m of the driven load, and in turn change its position theta m. Therefore, in motor drives, the most effective way for controlling the position or speed of the load connected to the motor is to control the torque of the motor directly. However, the torque control is expensive, due to the high cost of the torque sensor for motor torque feedback. The torque is directly proportional to the current under a constant field flux. This tells us that we can control the torque by using the current instead of the torque itself. Thus, the current control is important for the speed or position control of a motor. This is the typical configuration of controllers in the motor drive systems, in which the controllers required for position, speed and current control are usually connected in a cascade. The current controller must be placed at the most inner loop and has the widest bandwidth. Since the speed and position can be controlled through the current control, the response time for the current control must be the fastest among the three. Likewise, the response for the control of the inner loop should be sufficiently faster than that of the outer loop to improve the response performance and the stability of the outer control loop. For example, the bandwidth of the current loop needed to be at least 5 times wider than that of the speed loop to ensure that the current control will not have any influence on the speed control performance. Closed-loop control is a type of control that adjusts the control input by the feedback of the output. The closed-loop control is generally used to control the position, speed, current, or flux in the motor drive systems. The controller adjusts its control input to reduce the error between the output and the desired goal. Thus the role of the controller in the closed-loop control is very critical to the system's performance. There are several types of widely used types of the feedback controller in the motor drive systems. A widely used controller in motor drive systems is the proportional integral controller, PI controller, which is a combination of a proportional controller and an integral controller to achieve both a fast response and a zero steady-state error. Disturbances are always present in the control process. In motor drive systems, for example, the back EMF acts as a disturbance on the current control, and the load torque acts as a disturbance on the speed and position control. Feed-forward control is an effective way to rapidly eliminate the effect of the disturbance on the output. The feed-forward control predicts and compensates for the disturbance by adding it to the control input in advance. In motor current, the performance of the current control could be significantly improved by the feed-forward control, which compensates for the back EMF that acts as a disturbance on the current control. For motor speed control, the performance of the speed control could also be significantly improved by feed-forward control for the load torque. The PI controller has been widely used in motor drive systems as the controller for the current, speed, or flux linkage control, because it could give a satisfactory performance. The performance of the PI controller depends heavily on its selected gains. Thus, it is very important to select appropriate gains of the PI controller for obtaining a satisfactory performance in a given system. When designing a control system, we should consider the three specifications: stability, response time, and steady-state error. First of all, the whole system, including the controller, must be stable. Therefore, the stability is the most important requirement for the design of a control system. We can measure the relative stability of a system by examining the gain margin and the phase margin obtained from the Bode plot of the frequency response. If a closed-loop system is stable, both the gain margin and the phase margin need to be positive. In general, the phase margin of 30 to 60 degrees, and the gain margin of 2 to 10 decibels, are desirable in the closed-loop system design. How quickly a system responds to the change in input is an important measure of the system's dynamic performance. The speed of response of a closed-loop system may be proportional to its control bandwidth. Thus, the control bandwidth is a measure of the speed of response. Generally, the wider the system's control bandwidth, the faster the speed of response is. However, if the control bandwidth of a system is too large, the system may be sensitive to noise and become unstable. This control bandwidth is mainly dependent on the proportional gain of the controller. Thus, we need to adjust the P gain to obtain the desired response speed. Steady-state error is defined as the difference between the desired value and the actual value of a system when the response has reached the steady state. We can calculate the steady-state error of the system using the final value theorem. In the next videos, we will deal with these topics: current controller design, speed controller design, power electronic converter, simulation of direct current motor drive system, by using MATLAB and Simulink.